The metric tensor should begin with one physical question. What stays the same when geometry bends? Start from distance first, then build the symbols. Mark 2 points on a flat sheet. Call them A and B. Draw the line on the sheet between them. That line has a material length, which we call L. Now bend the sheet. Do not stretch it. Do not tear it. The same ink line is no longer straight in the outside picture, but its material length on the sheet is still L. This is the first invariant. The outside coordinates of A and B may change. The shape seen from outside may change, but the intrinsic distance measured along the sheet is the same. For a finite distance, imagine cutting the yellow curve into many tiny pieces. Each tiny piece has a length ds. Adding all those tiny pieces gives the total length from A to B. On a flat Cartesian sheet, each tiny ds is easy to compute. The axes are perpendicular. The units are equal, so locally we get Pythagoras. ds squared equals dx squared plus dy squared. On a curved surface, the same idea survives, but the local ruler can change. The structure may be locally scaled. The structure may be locally tilted. The metric records this internal measuring state. It does not mechanically force the surface. The coordinate grid bends with the sheet. At a chosen point, the two coordinate curves have two tangent directions. Those local tangent directions are the local axes of the surface. Now the important difference appears. On a curved surface, the two local axes do not have to be perpendicular. They can be oblique. They can also have different lengths. We call the position of the surface R of u and v. Then the two local axes are EU equals partial R over partial u, and EV equals partial R over partial v. These are not abstract symbols. EU is the direction in which the point moves if only u changes. EV is the direction in which the point moves if only v changes. Now take a tiny step on the surface. The numbers du and dv tell how much we move along those two coordinate directions. So the tiny vector is dr equals EU du plus EV dv. This is the same idea as the flat formula, but the axes are now local and possibly oblique. The numbers du and dv are contravariant components of the displacement. They are the coefficients multiplying the local basis vectors. Why the word contravariant? Because if the local basis stretches or tilts, the numerical components must change in the opposite way, so that the actual vector dr stays the same. Now we measure the length. Distance squared is still the dot product. ds squared equals dr dot dr. Substitute the expression for dr. We get au du plus ev dv dot au du plus ev dv. Now distribute the two brackets slowly. First term times first term, eu du dot eu du. First term times second term, eu du dot ev dv. Second term times first term, ev dv dot eu du. Second term times second term, ev dv dot ev dv. Those four products become eu dot eu times du squared, eu dot ev times du dv, ev dot eu times dv du, ev dot ev times dv squared. Because the dot product is symmetric, eu dot ev equals ev dot eu. So the two mixed terms combine. This gives ds squared equals eu dot eu du squared plus 2 au dot ev du dv plus ev dot ev dv squared. Now we give names to those three dot products. GUU equals EU dot EU, GUV equals EU dot EV, GVV equals EV dot EV. This is the metric. It stores the local lengths of the coordinate axes and the local angle between them. The distance formula becomes ds squared equals GUU du squared plus 2GUV du dv plus GVV dv squared. In matrix form, the metric is the array with entries g, I, j. The diagonal terms measure the squared lengths of the axes. The off-diagonal term measures how oblique the axes are. Now we can explain covariant components. Start with the contravariant components du upper I. These are the coordinate steps. Apply the metric. du lower I equals gij du upper j. This lowering of the index turns coordinate steps into measured components. Geometrically, the covariant component is what the vector reads when tested against the local measuring direction. It contains the effect of axis lengths and axis angles. Therefore, the same distance can be written in two equivalent ways. ds squared equals du lower I du upper I, or, after substituting the metric, ds squared equals gij du upper I du upper j. That is the metric tensor. It is the object that converts coordinate motion into actual measured distance. In flat Cartesian coordinates, the metric is the identity matrix. We write this as gij equals delta ij. The symbol delta ij is called the Kronecker delta. It is 1 when I equals j and 0 when I is different from j. That is why the formula collapses back to Pythagoras. On a curved surface, the metric can change from point to point. So the local ruler of geometry changes as you move. This is the physical meaning. The metric tensor tells every point of space how distances are measured there. It records the local measuring state of geometry, scale, angle, and intrinsic distance.